I'm Rumi, and I'm here with Olivia and Fadheel for the presentation of our Thermofluid project. It is about the design and simulation of a modular saturated steam generator for small-scale food processing applications. Next. Next. Okay. For the introduction, our background is that small and medium-sized enterprises in the food processing sector faces significant challenges in providing reliable, affordable, and energy-efficient thermal systems. They require saturated steam for their unit operations. However, commercial steam boilers are often too large, too expensive, or too complex, and there's a clear need for compact, modular, and cost-effective steam generation systems that can provide flexibility and efficiency. Next. Okay. So this is the process overview, the process of the whole system. The steam generation system is built to deliver consistent, reliable performance for small-scale industrial operations. At its core, the unit is designed to produce 25 kilograms of saturated steam per hour, reaching steam temperatures between 150 degrees Celsius to 160, which corresponds to a working pressure of around 4.5 to 6 bar, and the daily steam output reaches 150 kilograms, assuming a standard 6 hours operating cycle. From the process itself, we see that the raw water is then pumped into the heater, which is an economizer. It is so that the water is being heated before entering the boiler, and in the boiler itself, it will be heated fully to reach saturated temperatures, and then the drum separator will separate the steam and the water, and then we will have the steam as our final product. Okay, next. Okay, now these are all the tools that we use to develop all of our simulations and optimization. Aspen HYSYS for the PFD, MATLAB for the mathematical modeling and optimization, SolidWorks for each and every component of our models, ANSYS for thermal modeling, and then AutoCAD Plan for PNID diagram. Okay, next.
All right, so the next is before we entering the PFD using Aspen HYSYS, I will explaining about the energy demand calculation, which can be drawn from the boiler enthalpy calculation to estimate the what value actually the energy needed of the system. We calculated the heat duty of the boiler using the equation Q equals to m dot times delta H, where m dot is the steam mass flow rate and delta H is the enthalpy difference between inlet water and saturated steam, which we um, can get the enthalpy value from thermodynamics table. And for more complete data, we have put in the project report actually. This Q value was then multiplied by the operation time, 6 hours a day, and 5 days a week, to determine the weekly and monthly energy requirement for the system, like the tables in this slide. And next slide. Okay, so we move on to the process flow diagram using Aspen HYSYS. The steam generation system begins with feed water entering a vertical centrifugal pump, where its pressure is increased from atmospheric condition to 480 kPa, ensuring sufficient driving force for the subsequent thermal stages. The pump consumes approximately 12.60 kilojoule per hour, and pressurized water then flows into the economizer, a heat recovery unit where the water water heat is preheated using residual energy from the boiler flue gases. And then the feed water exits the economizer at 70 degrees Celsius, reducing thermal load and on the main boiler, optimizing fuel usage. The next The preheated water enters the boiler. Hello. Uh, okay. And then, so the steam exits the boiler at temperature of 151.8 degrees Celsius. The steam is then directed into a steam drum separator. Okay, so the next is in the steam generator model using Aspen. Two different fuel scenarios were analyzed, which is LPG based combustion and biomass based combustion, both mixed with air composed of 20% of oxygen and 80% of nitrogen, and then injected with moisture H2O for humidification and steam quality control. Simulation 1, LPG combustion. The fuel used, this simulation consists of 70% of propane and 30% of butane when burned with oxygen. So the output is flue gases, which is CO2 and H2O and N2, and the process steam, which is saturated at H2O vapor at 152 degrees Celsius. And then we using biomass wood pellets. Is modeled with composition of 57% carbon, 5% hydrogen, and 38% of oxygen. Upon combustion, carbon reacts to form CO2 and hydrogen forms H2O with internal oxygen contributing to the reaction. And also the output is flue gases CO2 and H2O and N2, and the process steam saturated H2O vapor. Yeah, next. Okay, then the most important one is the piping in instrumentation diagram or PNID of the steam generation system illustrates. Designed for batch food processing application, we use AutoCAD 3D plan for this. The, actually, the diagram is not the most different from Aspanasis, but uh, any differences with the text and the valve taking a naming. For example, the process begins with centrifugal feed the water pump with the tag of P 001 and so on through an economizer. We take special and unique and take and so on. So actually, this PNID is equipped with multiple globe valve for manual isolation and one strategically placed control valve. Um, the key instrumentation also elements are clearly take and include temperature indicators like TAH along the economizer and steam lines, level transmitter LC, and flow transmitter. These measurements and control devices are essential for maintaining a safe and efficient operation. Okay, thank you.
Okay, for the next one is the component design and technical drawing. So basically, our boiler system consists of four up to five key components. The first one is furnace, a compact cylinder furnace designed for wood pellets. It ensures efficient combustion and allow easy as removal. Uh, I think this is ideal for a low pressure fire tube boiler. And the second one is steam drum. This is serving as a boiler cell, and the steam drum separates steam from water and maintains steady state pressure for consistent steam output. And the next one is insulation. When we use insulation, we choose for fire breaks in the furnace to retain heat effectively and support stable combustion over the time. For the heat exchanger, we choose to use a parallel flow heat exchanger. we choose this because of its simple construction, compact size, and easy of maintenance. And we believe this is quite suitable for our small scale system, especially for small industry. The next one. And the system requirement and specification. We use MATLAB to help us in showing us the system and the boiler work. And we try to use time spent for about 30 minutes. And this system was simulated over 30 minutes using MATLAB. And when we begin, we assume that there are 10 kilograms of water inside the boiler, and within just 3.1 minutes, the water reached saturation temperature at 150 degrees Celsius, as shown in the second graph. That this is indicate that a fast startup, which is suitable for batch operation. And for the from the third graph, we can see that steam production rate rise quickly and stabilize at around 27 kilogram per hour, or equivalent to 0.007 kilogram per second. In the first 20 minutes, the system produced around 7.23 kilograms of steam, and by the end of 30 minutes, it reached around 11 up to 12 kilograms. The heat transfer graph at the top also show an initial high input, peaking at 35 kilowatt, then stabilizing around 22 kilowatt on average. In total, the system used around 40 kilojoule of thermal energy, which is equivalent to 11 kilowatt hour. With this, we achieved that the boiler efficiency of our system is around 80%, which is quite efficient for a small scale unit. And finally, based on this performance, we can estimate that that our system can generate around 25.2 kilograms of steam per hour, which can meet the target rate effectively. Okay, the next one is the component design and technical drawing. If you want to need to look up a detail or the more components about our system, it is attached on the report, but today we just uh, see the today we just explain it briefly. Okay, then the next one is thermal modeling and system behavior. On the left one, it is the two-phase boiling simulation. The simulation models the nuclear boiling where the water reaches saturation and begin to vaporize. This is a 2D domain, was used to simplify our computation and capture the key radial heat transfer behavior. The heating surface was set up at 300 degrees Celsius with an adiabatic boundary to ensure all heat is absorbed by water. Then the volume of fluid model was used to track the liquid vapor interface and simulate bubble formation realistically. We also enable phase interaction model and surface tension effect to capture boiling dynamics. And also we also use energy equation to activate the drive of the phase change. Then the next simulation, the on the right one is radial temperature distribution. The simulation show the vapor formation once the saturation point was reached. A radial temperature distribution up to 6,000 Kelvin near the heating wall that confirms strong heat input and supports the design feasibility. However, the real simulation cannot be shown here due to limited computational resource on our laptop. Therefore, the simulation, we only snap some photos about the simulation. And then the next one. Okay. For the heat source and fuel evaluation, to compare we can see that there are two choices about the fuel. The first one is using biomass, and the second one is using LPG. But we have already mentioned all the pros and cons about using each side, and it can be seen in the table here. Okay, we also use MATLAB to demonstrate the heat source and the fuel evaluation on our system. The top bar chart showed that monthly fuel consumption of wood pellet reached nearly 700 kilograms, while LPG only requires about 260 kilograms. This gap is due to LPG higher caloric value, which is roughly 3 times greater than the wood pellet. However, high consumption does not always mean high cost. The bottom chart highlights that despite using more mass, wood pellets cost less than 1,000 per month, compared to LPG, which can cost almost $250 per month for the same steam output. This clearly makes biomass cost more in economical side, especially when operating under strict monthly budget. Financially, biomass is more sustainable solution for producing 25 kilograms of steam per hour, which running in 6 hours a day and 20 days in a month. And the next one is our design optimization. So we choose to use economizer to make our system more to make our system better than before. So our economizer features a helical coil heat exchanger with 10 turns of tubbing. Each has around 30 millimeter out of the outer diameter, with a total heat transfer surface area of approximately 1.2 square meters. It is designed to recover waste heat effectively within a compact footprint. Functionally, the system preheats with water from 25 degrees Celsius to 80 degrees Celsius before it enters the boiler. This reduces the fuel consumption, lower thermal stress, and also significantly shortens the startup time. And apart from that, it's also improving overall system efficiency. We believe that this is quite ideal for our modular and small scale system where space and energy efficiency are priorities. This economizer not only can enhance performance but also contribute to more sustainable and cost-effective steam generation system.
Okay. All right. So for conclusion, the system delivers 25 kilograms per hour of saturated steam at 151 degrees Celsius and 4.8 bar, operating efficiently within space and pressure limits. The two fuel options evaluated is that LPG is cleaner for combustion and faster response. Biomass has a lower monthly fuel cost with 40% savings. And thermal modeling using ANSYS Fluent helped optimize that distribution and installation. And an economizer integration improved energy efficiency and reduced boiler load. And then control and instrumentation enhance safety and system reliability. And for the recommendations that we use biomass as our primary fuel and LPG as backup, and then strengthen insulation and maintain safety valves. Okay, that is all for our presentation. Thank you very much.